Welcome, everybody. Today's speaker is Shreyasi Datta from the University of Michigan. She'll be speaking on p-Adic Diophantine approximation with respect to fractal measures. Go ahead.
Thank you. First of all, I want to thank the organizers for giving me this opportunity. Today, I'm going to talk about a joint work with Victor Beresnevich and Anish Ghosh. So since I'm going to talk about p-Adic Diophantine approximation, so let me just quickly talk about QP. So QP is a completion of p-Adic norm that you can define on Q. So this is a chain of sets that we will be interested in. And QP is a totally disconnected space, so you can think about something like this. Yeah, so this is Q7. So this
the balls are not really tangent, right? They are far from.
Right. Yeah, they are far from. Yeah, they are not connected to each other. Okay, so this Q is dense in QP, and moreover, Z1 over P is also dense in QP. So since Q is dense in QP, you can talk about approximations of numbers in QP by rationals. So you may ask, is there any Dirichlet type theorem? The answer is yes. Before getting into that, I just want to point out that there is a difference between approximation in case of R, where you look at the rationals as a fraction of C, and in fact Z is discrete in R, but whereas here Z is actually dense in the unit ball of QP. So I'm going to denote the unit ball by ZP. So the right Dirichlet's theorem is something like this. So you take any x in ZP, then for all Q large enough, you can always get solution to this two inequalities. So you have Qx plus Q naught p-Adic norm less than equal to 1 by Q square, and you take the infinity norm of Q and Q naught and say that that is less than capital Q. And this one should have a non-zero integer solution. So the difference is that, well, here you have to have both Q and Q naught, unlike a real approximation. And the reason is that integers are dense in unit balls, so you cannot just take like infinity norm of Q. And since you are taking infinity norm of Q and Q naught, so you would expect that the power here should be 2 instead of 1. Okay, so now that we know Dirichlet's theorem, you can also do it in QPN. You can talk about all sorts of number theoretic objects that people are generally interested in. So from Dirichlet's theorem, you can talk about, you can define very well approximable. More generally, you can talk about Dirichlet exponents. You can talk about badly approximable vectors. You can also talk about improving. So these two come from a corollary of Dirichlet. You have one inequality. If you use these two inequalities, you can talk about, as a consequence, you can say that qx plus q naught p is less than 1 by the norm square for infinitely many q and q naught. And from there, you can improve that and talk about variable approximable or Dirichlet exponent. And you can also say that the points for which it doesn't happen, you cannot improve that inequality. You can say that those are the badly approximable vectors. And then also you can talk about singular vectors. And more generally, you can talk about uniform exponents. So for today's talk, I'm going to mostly talk about variable approximable, and then I'll also talk about badly approximable briefly.
But you're always saying vectors, so you want high dimensional extension of your Dirichlet theorem.
Right. Yeah. Yes. Okay, so to begin with, one can very easily check that, like if I denote lambda n to be the Lebesgue measure, in Rn or in QPN. So I'm going to talk about both of these fields simultaneously just to point out the differences and how the methods in Rn sometimes don't work in QPN. Okay, so one can show that lambda n of variable approximable is 0. So then next question is what if you restrict to a submanifold? So Mahler started this question that, okay, if you take a parabola and look at the variable approximable vectors inside the parabola, then whether the measure is 0. This was proved by Sprinjuk in 1960s, and he then like made another conjecture, which is that if you take any analytic manifold which is not contained inside any affine hyperplane locally, then the variable approximable should have measure 0. So this conjecture was proved by famous work by Kleinbock and Weiss. So this is in Rn. So the setup is that you have a function f from, so since I'm going to talk about both of these fields, I'm just writing f. So some open set of ft to fn. And let's assume that f is not flat and f is analytic. Then if you look at f star lambda, the variable approximable with respect to this measure must be 0. In fact, they proved it for more general setup, not just for analytic.
What is capital F here?
F is R for now. But I'm also want to mention that Kleinbock and Tomanov proved this when f is QP. And so this is this conjecture, which is referred as Sprinjuk conjecture, is proved for both Rn and QPN. Okay. Now that we know that volume measures on submanifolds satisfy this property that variable approximable is 0, So I'm going to refer to any measure which satisfies this property as extremal. So mu is extremal if mu of, so mu, let's say a measure in Rn or QPN. Then if mu of variable approximable is 0, then that's the definition. Okay, so now question is, when can you say, other than this kind of measures, when can you say that the measures are extremal? Okay, so next, Kleinbock, Lindenstrauss and Weiss. I'm just going to write KLW. In 2005, they found geometric conditions on mu, a measure in Rn, such that mu is extremal. Okay, so they call such measures friendly. I'm going to define them in a bit, but just want to first write it down. So mu is friendly, implies that mu is extremal. Kleinbock and Tomanov in 2007, they proved the same result for QPN. And I want to also mention a relatively recent work by Dash, Fishman, Simon, and Urbanski, where they in fact relaxed the condition of friendliness. So they defined a weaker kind of measures for which also they can say that they are extremal. So it's a larger class of measures. They call it weakly quasi-decaying. I'm not going to define it, but just for record, I'm going to write it down. So mu is weakly and this is for Rn. Okay, so naturally the next question is what are these friendly measures, and whether the previous measure that we talked about, f star lambda, whether that is a variable whether that is a friendly measure or not, and is there any way to cook up friendly measures? Okay, so for that I need to define what friendly measures means, and before I define that, I need to define a certain property of functions of any CK function that I'm going to, that are the main that are going to play the main role in this talk. So good maps with respect to a measure. So if you take, let's say, a function g, it doesn't matter which field you're talking about, the definitions are all same. In fact, you can talk about a map from some metric space to a field and talk about good maps. So I'm just going to write for QP, since we're talking about QP. So G is a map from QPD to, let's say, QP. Is called C alpha good so let's say this is a map from open set of QPD. On U, if you look at all those, so if you look at any ball, so this is your U, if you take any ball that is centered at support of mu, then all those points for which the function is small with respect to its essential supremum should have small measure. And if you, so I also said absolutely good. So if you, instead of essential supremum, if you replace this by just supremum norm, then that's going to be absolutely good. So if something is absolutely good, it's going to be good as well. For example, you should keep in mind, I mean, maybe you can think about polynomials with respect to Lebesgue measure. Okay, so now it's a good time so I talked about good maps. Now it's a good time to talk about friendly measures. Okay. So there are three properties. So mu is a measure in, let's say, QPN. There are three properties that mu must satisfy. First, it must be doubling. So I'm going to write the term that they are using, Federer. So this was defined in Kleinbock, Lindenstrauss, Weiss work, KLW. So Federer means that if you take any ball centered at support, let's say of radius r, and if you dilate it by, let's say, any number 5 or 3, then the volume of that bigger ball and volume of the smaller ball, the volume must not be growing like, it must grow uniformly. So if I take this as 3r, then mu of bx 3r divided by mu of bxr must be less than some d. And if you change 3, then d can change, but for all r, you should have the same d. Then the second property is that it must be non-planar, which is one of the, okay, so non-planar means that the measure cannot be supported on any affine plane. So mu of any affine plane must be 0. And that was the case when you were working with f star lambda. Saying that it is non-flat is same as saying that it is non-planar. And then the third most interesting property is that any affine map with respect to this measure must be good. And similarly, you can, if you replace this good by absolutely good, you say that that is absolutely friendly. Okay, so you can actually think about the last, so last condition is called decaying condition. So and another way to think about decaying is that if you take any ball and if you intersect that ball with any affine line, sorry, so okay, so if I take this line and if I look at any small neighborhood of that line, so you can talk about from any point x, you can talk about the distance of x from that line. That is an affine map. So saying that the affine maps are good means that you want to make sure that mu of b intersection. So if I say that this is L epsilon, and this line is L, then mu of B intersection L epsilon should be small with respect to mu of B. So this should be epsilon, and this is the essential supremum. There must be some constant, so I will write this. So these two are equivalent. You can say either that affine maps are good, or you can say that this is a definition of decaying. Okay, all right. Now question is, okay, we have definition of friendly. We want to know which measures are friendly. Generally, it's not so easy to say whether just by looking at a measure, whether it's friendly or not. Okay, so I'm going to just kind of draw and draw a diagram and say that what we know. So okay, so Kleinbock, Lindenstrauss and Weiss. So they showed. Now everything I'm talking in case of Rn. So they showed that any Lebesgue measure is friendly. Then you can take push forward by non-flat maps. They are also friendly.
Are they still real analytic? Must be some conditions, probably.
So
differentiable.
They are differentiable. Yeah, they are all CK for some K. Yeah, so throughout my talk, I'm only talking about functions which are CK. Okay, and then also they showed, so this is one theorem, then another theorem, they showed that if you take any Cantor set, and if you look at the Hausdorff measure, then if the Cantor set satisfies, so if the fractal satisfies open set condition, and if the similarity maps that give you the fractal are irreducible, meaning you don't have any affine plane invariant under the similarity maps, then those fractal measures are also friendly. So so let's say K is Cantor set, then these are friendly. Not only that they are friendly, but actually they show that they are absolutely friendly. So remember I said absolutely friendly implies friendly, because absolutely decaying implies decaying. So they show that actually these kind of measures are absolutely friendly. And then also they showed that if you take, now the setting is that if you take F, again same as before, non-flat CK function, if you take mu, which is friendly or absolutely friendly, on RD, and you look at F star of mu, then it has to be friendly. So there is a difference between, so if I call this one as theorem 1, theorem 2, theorem 3. So theorem,
is D supposed to be greater than N or something? Or?
D is less than N.
But then you say non-flat and also I'm just
yeah, so you have a map from, so you can think about a curve in case of, let's say, R3. So you have a curve inside R3, so it's a map from R to R3. And if the curve is not inside any affine plane in R3, then you say that the map is non-flat.
But then if the dimension is less, would it not become planar, like image and all? So
Yeah, so if the image is inside a plane, then you say that that is flat, which is not what we are talking about.
okay.
Okay, so the difference here is that like here you are pushing forward the Lebesgue measure, and then you are saying that that is friendly. Here I'm pushing forward by an absolutely friendly measure and saying that that is friendly. So you cannot actually like make it just friendly. Like you cannot say that, oh, if you start with a friendly measure and it push forward by this nice functions, then the push forward measure is also friendly. That is not true. You can like take, for instance, RD to RD. So let's say R3 to R3. You can take the map XYZ going to XY minus Z. And so this is a non-flat map from R3 to R3, but it takes the, if you look at the volume measure on XY, then it goes to a plane in R3. So clearly the volume measures are not absolutely friendly. Volume measures on smooth manifolds are not absolutely friendly. So you cannot make it better in terms of friendliness. Okay, so this was a situation in case of in case of R. Now, in case of QP, this theorem 1 is proved by Kleinbock and Tomanov for QP. And this theorem 2 is also proved for QPN by Kleinbock and Tomanov. And in that same paper, they conjectured theorem 3. So the reason that this is not the proof for Lebesgue measure is not same as the proof for this kind of absolutely friendly measures. So you can think about fractal measures, and if you take the push forward of them, then the proof uses mean value theorem very extensively. So it's not at all clear how the proof in case of R would work for this kind of setup. Is there any question? Okay, all right. So let me write down our theorem. So so this is a joint work with Victor Beresnevich and my PhD supervisor, Anish Ghosh. Okay, so the conjecture is true. Okay, so let me, so let's say this is theorem A. So I want to talk about what is really going on, or like what is the main idea in theorem A. So if you want to prove that f star of mu is friendly, then let's go back. So you have to prove these 3 properties about f star of mu. And the crucial property, or the most non-trivial property, is to show that f star mu is decaying. And so the goal is that f star mu is decaying, which actually follows from, so decaying for some
Or can you remind me again what is my conjecture? What is the assumption on mu in this theorem?
yeah, so the assumption is that so maybe I should write it down. So
Has been a long time.
yeah.
You can just write the theorem that we proved.
So yeah, so HS is a fractal measure. Which satisfies open set condition. And also the similarity maps are irreducible. So I'm just going to write irreducible. Then if you take an open set of QPD and get the map F from QPD to QPN. And if you look at F star of HS, then conjecture is that F star of HS must be extremal.
Mm-hmm.
So since you already proved that it's enough to show that it is friendly, so we want to show that under this. Also, we know that these measures are absolutely friendly. So really, this conjecture is to show that if you start with an absolutely friendly measure, and then if you push forward by nice functions, you get a friendly measure.
Okay, and the proof of absolute friendliness just follows the real case. Or is it what?
No, so we want to prove that f star of HS is, or f star of mu is friendly. That's the main.
Yes, but we already know that mu is absolutely friendly.
Yeah, we already know that HS is absolutely friendly.
Mm-hmm.
Okay, so really the goal is to show that f star of mu is C alpha decaying. When you know that, so now on, the assumption is always that mu is absolutely friendly. And F is not flat. Okay, so what was absolutely decaying of a measure? It means that if you take any affine map, then it must be good, right? So first of all, if I have a map from QPD to QPN, then I have F in many coordinates, so F1 up to Fn. So showing this goal is really to show that if you take any, so if you look at any affine map with respect to f star mu, that means you are looking at all linear combination of these coordinate functions with respect to mu. So this here is implied if we can prove that any C0 plus C1 F1 plus Cn Fn is absolutely C alpha good with respect to mu. For some Cn alpha. Okay. So this looks like something like more basic than all those terms and like all that conjecture and theorem. So it's really, if you have a fractal measure and if you push forward and if you look at all the linear combination of coordinate functions, they must be C alpha good with respect to this fractal measure. Okay, so this is actually now a theorem. So I should say theorem. Let's say theorem B. And I want to emphasize that although we have we proved the conjecture, but really our work is to show this theorem because it has other applications. So for instance, if you instead of non-flat maps, if you, let's say, take a flat map, right? So let me say theorem C. So let's say mu is absolutely friendly. And F is a map from QPD to an affine plane. Such that although the map is not flat inside QPN, but it is somewhat, L is the intersection of all affine subspace where the image is. So L is the least affine subspace where F is inside. So in some sense, it's saying that F is non-flat inside L. And then the conclusion is that if F star of mu is extremal, if and only if L is extremal. In fact, you can also talk about Diophantine exponents, that their exponents are same. And more interestingly, why we actually start. So we did not start with this project. Like our goal was not initially to prove such theorem, but rather we were working on working with badly approximable vectors. So I want to just briefly talk about what is, this is an ongoing work. So if you look at badly approximable vectors in case of inside Rn, the dimension of that is the dimension of the ambient space. So you can say that, okay, what happens if you take a manifold and you look at the badly approximable vectors inside that, where the dimension of the manifold, Hausdorff dimension of the manifold is same as the dimension of this intersection. And this was proved by Viktor Beresnevich in 2015, I believe. And then more generally, you can ask, okay, if you take any friendly measure, and if you look at the badly approximable vectors, if you intersect with the support, what is its dimension, or if at all there is any point inside that. So using theorems by Bazian, Harap, Nesherim, and David Simmons in 2008. Their result was in 2018, where they show that if you want to show that a bad inside any other measure is waning, which is stronger than saying that the dimension is full, is to show that you take fractal measures and you intersect you take fractals and you intersect them with the badly approximable vectors, and you should have that to be non-empty. So if you can show, so this was done in a recent work by Viktor Beresnevich, Nesherim, and Lei Young. So this was 2021. That if you take for any if you take any alphas regular measure, which are weaker than friendly measures or absolutely friendly, Then, and if you, let's say U is an open subset such that U intersection support of mu is non-empty, then F inverse bad intersected with support. Okay, so you have a map from U to Rn. Then this is non-empty. And that is same as, I mean, using this previous work, you can say that that is same as showing that it is absolutely winning. So if you want to work with such a setting, you have to use, so they are using quantitative non-divergence, but with respect to some absolutely friendly measures.
So what is U? U is
U is an open subset of R.
R. Okay, so it's about a curve. Okay.
Yeah, it's for cars, right? Yeah, so they need to use quantitative non-divergence with respect to fractal measures or friendly measures. And for that, you need to know these kind of results, that if you take the linear combination of the coordinate maps, and then they must be good with respect to the fractal measure. So yeah, so using, so that is the reason why we started to work with this theorem B, and also we could prove this conjecture. Okay, so is there any question?
I have a question. I'm sorry.
Yes.
What is the purpose of those coefficients C0 through Cn in there in theorem B?
Yeah, so like you want to show that this kind of maps, F star mu's, are decaying, right? And decaying means that the affine maps, so if you take C0, C1, X1 plus C up to Cn, Xn, then these maps must be C alpha good with respect to F star of mu. So that is same as saying that these functions must be C alpha good with respect to mu.
I see. And then the C and the alpha would depend on the on C0 through Cn, or is it?
No.
Okay.
Yeah, so that is a good point, that we don't want that dependency on C and alpha.
I see.
Okay, all right. So now I should talk about QP in last probably 10 to 15 minutes. Okay, so what is the problem really? So okay, step one, and probably I can only talk about step one. Right, so you have, now forget about everything. So you have a map G from and I'm only going to talk about dimension 1 instead of higher dimension. So my maps are from, the maps are all cars, although the theorems that we proved are for higher dimension. Okay, so B is open ball inside QP to QP. Standing assumption is that mu is absolutely friendly. We want to really know what are the conditions. So we know that the initial theorem has a condition that G is non-flat, but we really want to break it down and see, like, if you start with any CK map, then what are the conditions on G such that you can say that G is absolutely good on B. Okay, so okay, so now I should mention how the proof in real case works and compare it with our situation. So okay, first of all, if you just start with, this is just basic real analysis. Like if you start with, let's say, a function f from a ball of radius r inside an open set U of, let's say R, and okay, so you have a map like this, which is CK. Then using mean value theorem, you can show that So let me call it lemma R. Using mean value theorem, you can show that infimum of fk, if k is a kth derivative, on this ball must be less equal to r to the power minus k, and then supremum norm of f on ball. Yeah, so I'm going to denote by single norm, the supremum norm. And this is a notation for infimum of fk of x, so b. So you can like intuitively think that, okay, if you take 0, 1, and if you take a and a plus 1 in 0 in let's say minus 2 to 2, then f of a plus 1 minus f of a must be some f prime of c. And so you can say that infimum of f prime must be less than 2 times the supremum norm of f. So it's really a basic real analysis. Okay, now what is the situation in case of QP? First of all, mean value theorem is not there, but well, you can talk about, first of all, what is the definition of differentiability? So you can just define differentiability as you would do in case of R. So like same definition, f prime, fi. But actually you can, since there is no mean value theorem, you can actually define stronger differentiability condition, namely this. So if you can define a map, which I'm going to denote by phi1 of f, it's called difference quotient on u cross u. So it's on a box, but not on the diagonal. So if phi1 of fxy is just f of x minus f of y divided by x minus y. And of course, this is not well defined for the whole u cross u. So you are defining it on everything but the diagonal. And then probably you have already guessed that the definition of f to be c1 is that this function should be extended to the whole u cross u. If and only if p1f is well defined on u cross u. And okay, so that means limit of p1 f xy is phi1 of f aa if x and y goes to a comma a. Okay, I don't want to get into more details about this like function. So the thing is that, okay, first you defined phi1 of f. So you started with a one-dimensional function, but phi1 of f is now a two-dimensional function. And then you define phi2, which will be on u cross u cross u. So that would be from QP3 to QP. And even if you impose the stronger condition on f, still it doesn't have mean value theorem. Okay, so what we should probably just work with like the definition of CL maps, CK maps. So note that because I define this phi1 of fxy in this manner, I can say something not really mean value theorem, but something which looks similar to mean value theorem, which is that f of x equal to f of y plus phi1 fxy times x minus y. So this in case of R, you would have this to be some f prime of c, but here you don't have that, but this is a function on two coordinates. And we are going to exploit that. We are going to use this definition. And yeah, in higher dimension, it becomes more complicated. You have to find the right like relations between this phi i's and in fact phi beta. And then you can show, so I want to just like write down the analogous lemma that you can prove in case of QP is that infimum of phi kf. Now phi kf is a multivariable function in bk plus 1. So b cross b cross b k plus 1 many times. So that must be less equal to r to the power minus k f of b. Now you can see easily that, well, this is definitely weaker than this lemma that we have for QP is definitely weaker than this lemma, because here I'm taking infimum over a like huge thing, and I don't know where exactly the infimum is attained. I know that some point it should be attained because it's compact, right? So I'm working with this weaker lemma. Okay, all right. So what were so let's go back. We were talking about the right conditions on G such that it must be absolutely good. Right. So if you look at, again, I'm going to write the real case here and the QP case. So in the real case, the conditions were that there were two conditions. One is that infimum, there should be a derivative such that it is bounded below. And this was also the feature in Kleinbock-Margulis's original work, that infimum of GK must be some s to the power r to the power minus k. And then supremum must be always all the other derivative, all derivative must be bounded above. So if you have G, a continuous function, a CK function, in fact, CK plus one function, such that these two conditions are satisfied and mu is absolutely friendly, then you can say that G is absolutely good with respect to mu. Okay, so what is the idea of the proof? So you want to show this kind of things, that x in P such that G of x less than epsilon, this is small. Now think about the set that you want to show that is small, and you have these two conditions. So maybe you can use induction and say that, okay, G prime satisfies these two conditions. It's not hard to see that these two sides will be, you can take G prime and instead of K, you will take K minus 1. And then you look at this part of like this, if I call this set to be, let's say, E epsilon G, this is my set, which is E epsilon G prime. And I want to use induction and say that, okay, this part is taken care of by induction hypothesis. And the other parts, you can take a look like smaller balls where the second derivative is bounded above. And you can show that these sets are also small. And then by covering argument, you can say that there are only, I mean, there is a multiplicity, so you can actually bound by finitely many of these balls. And that's the proof for R. Now, there is something very simple that goes wrong here. If you just try to imitate the same thing in case of QP, first of all, we don't have that previous lemma, which was stronger. So let's see what we can do. So we can say that, okay, forget about like using that stronger thing that you have in case of R. Maybe we can just work with QP and this weaker lemma, right? Okay, so let me just write it down. In case of R, the thing is that if you want to say that G prime satisfies these A and B, then you must have some relation between the norm of G prime with the norm of G, right? So let's see what happens. So infimum of GK, by hypothesis, we know that this is like bounded below. And then a very, of course, I mean, very trivial step shows that this is G prime K minus 1, which is by the previous lemma, the stronger lemma in R, is R to the power minus K minus 1, G prime of B. Okay, so that means I have a relation between, like, if I, so this is lemma R. So I can get a relation between G and G prime, namely this. Now, if I say that, okay, I don't have the stronger lemma, so let's just work with phi k and just like replace everything here gk by phi k, okay? So that would be probably the like thing that comes into mind. Okay, so here you will have pk minus 1 g prime. Okay, so you have this, instead of this lemma r, you have lemma qp, and this is the hypothesis, so that's fine. Now the problem is that this simple innocent step that was happening previously is no more true. So this is not correct. Like phi k of g is not same as phi k minus 1 of g prime. So I just want to point out what is going on. So if you do phi 2 of f x y z, or let's say, sorry, then instead of this being phi 2 of f, it's actually phi 2 of f evaluated at 2 points, and there's sum. So it's going to be x y plus phi 2 of f x y y, and that is the whole problem, because now you are taking infimum. So you want to compare this infimum of phi 2 of f, which is evaluated at x y z. It's a larger set. X y z are in B, and then you want to have some relation between this and infimum of p1 f prime x y, where x and y are in ball. Now, on one hand, you would expect that this thing should be smaller than this one because it's evaluated, the domain is large. But also on the other hand, you have here on this side, you have sum. So it may become 0, right? So you don't know. Okay, so that is the reason why you cannot just say that, well, these two are the just analogues of these A and B works. You have to impose another. So I'm going to stop by writing just the conditions. So theorem. Okay, so again, same assumptions as before. A must be that infimum of phi k g bk plus 1. So there should be a chain. Now, since you are using induction, so I don't know the relation between these two, but I'm imposing that, okay, let's say this is a relation that there is a chain of inequalities. So there are constants here, which I'm not mentioning. So last guy should be just gk. So this extra condition, and then the previous two conditions are analogous to real case, but not for gk, but phi k. Well, so you may, and then, okay, let me write, and then I can say last word. Then G is absolutely decaying. And start with G is a map from B to QP, a CK map, and radius of the ball is R, and what else? And mu is absolutely friendly. Okay, so first probably objection is that, oh, okay, you have an extra condition. So how are you going to prove something that did not have such a condition? So the idea is that, well, you say that, okay, these are the three conditions you need for any function G to be absolutely decaying. And then you show that the like polynomials satisfy this A, B, and C. And then that is the second step, which is to show that polynomials satisfy this A, B, C. And then the third step, which has its own complications, which I'm not going to get into, is that you want to now approximate phi k of P uniformly with phi k of G. And since P polynomials satisfy this ABC, you can show that the function that you are working with also satisfies these three conditions. So ultimately, your main theorem does not have any extra condition. And the problem is that, like, in higher dimension, when you are working with functions from like QPD to QPN, if you just like think about Taylor series, it was not known what is the correct error term, which we know in case of R. And since it's kind of like if you work in one dimensional, then only itself you have several other dimensions. So if you imagine in one dimension, you have other dimensions. So in 2 dimension, you have like, I don't know how to draw this. Okay. Like more dimensions for each coordinates. So you have a huge, like you have functions with huge domain, and you want to like find relations between them without, you don't have any mean value theorem or anything, but you can just exploit their definitions in different ways. And yeah. So I want to like stop here. Thank you very much for your attention.
Well, thank you, Shreyasi. Why don't we thank the speaker? And are there any questions or comments?
So can you expand on what you told about badly approximable vectors and winning properties? So you need something like this to prove analog of Beresnevich, Nisharim, Young for QP?
Yes, yes. So you need, so they are using quantitative non-divergence with respect to fractal measures. And in the quantitative non-divergence, one of the conditions is that the linear combinations, the coefficient maps, the linear combination of coefficient map must be C alpha good with respect to the measure. So we need this theorem. Yeah.
Mm-hmm. Okay, so the bottom line is that you have a theorem which is a p-Adic analog of winning property of badly approximable vectors and curves.
Right. So this is ongoing. Yeah, where we are proving for QP. In fact, we can also prove it for I don't want to say it, but like we can possibly prove it for QS, where S may contain infinity or may not contain infinity.
And can you put different weights?
Yes, you can put different weights as well.
Okay, very nice.
Hi, Shreyasi.
Hi.
Great talk. I have quite a few questions.
Mm-hmm.
First, is this new proof sort of gives a new derivation of the proof over R?
Yes. Yeah.
Oh, okay.
Because yeah, that's a good point. So I just want to quickly say that this like definition that I said for like CK maps in case of QP, that is stronger in QP because there is no mean value theorem. But in case of R, this definition is same as the usual definition.
And maybe what about FP function fields?
Right. Okay.
That's probably should be even more interesting if it works now.
So whatever I'm doing, I don't use any thing about the characteristics. So it should work. I mean, it must work for any ultrametric setup.
Another thing, you mentioned fractals on QP. Can you elaborate on this? Like, what are the interesting examples? Because it's a totally disconnected space to begin with.
Yes, right. So if you just look at let's say 3. Yeah.
Okay, Q4 is great.
And so you know that all the elements can be written as, or let's say Z3. So all the elements are like starting from 3 to the power I 0 to infinity. And where AIs can be 0, 1, and 2. So you can say that the fractal is where AIs take only 0 and 2.
Isn't that a set of positive measure in Z3?
Why?
Don't you have some of 2/3 or something to the I? I need to.
Well, at every stage you have 2/3, but then you multiply these 2/3 together, so it goes to 0.
I see.
Yeah.
And like in the counter set in the real line, I think it's
Right.
the same.
Okay, and the last question, because I took too much. Okay, thank you. The last question, you mentioned the covering theorem.
Right.
And the work of Kleinbock, Alon, and Barak, it was utmost important that they use the Beresnevich covering theorem.
Right.
Because when you use the general covering theorems like Vitali, you move the center points, and then you ruin your fractal. So what are you using? And Beresnevich is very specific for RD, essentially. Like there is some fancy theorems about manifolds, but it's only working on RD in the end. So what exactly are you doing?
We are using Beresnevich covering, which works for QP as well.
Are you sure?
Yes, I think, yeah.
So this is actually a fine point. Yeah, I think QP satisfies the Beresnevich covering. One can prove it. But in the paper with Tomanov, we actually made the wrong statement, saying that every ultrametric space has the Beresnevich covering properties, and this is not true.
Yeah, right, that's not true.
So you need some additional argument to make sure that you have it. My apologies.
Okay, thank you so much.
Other questions? Well,
I just want to say that it was a very nice talk, Shreyasi. Thank you, very lucid.
Thank you.
Thanks for joining us this late hour.
Yeah, it's pretty late in India. I guess it's almost 12.
well,
It's 11, close to
okay.
11.
well, if there are no other questions or comments, why don't we thank Shreyasi again? And we shall see you next week.